Hi everyone, I'm Romain Loiseau, and I'll present you the work we did with Tom Monnier, Mathieu Aubry and Loïc Landrieux, entitled Representing Shape Collections with Alignment-Aware Linear Models. Imagine you have access to a large, unstructured collection of 3D models and want to understand its content better. Browsing through the collection manually and identifying groups of related shapes would be a time-consuming approach. We propose a principled approach to automatically group shapes and summarize them using a prototype shape associated to a linear deformation model. Our goal in this paper is to summarize and understand large shape collections such as ABC and ShapeNet by offering an easily viewable summary of them in an unsupervised manner, allowing us to perform downstream tasks such as clustering and few-shot semantic segmentation. This is a difficult problem because the distance between shapes may be difficult to define using standard 3D point cloud distances, such as chamfer distance. For example, we want the distance between all of those chairs to be zero, even if they differ by rotation. It's also difficult to compute the average of several shapes, especially if they are not aligned. For example, chairs can have arms or not, and the average will end up fuzzy. To answer these issues, we introduce linear shape models, a powerful and expressive data structure in three-dimensional space that allows us to meaningfully summarize sets of shapes. At first, we can simply define a linear shape model as a center shape defined as a 3D point cloud, which we train by minimizing the reconstruction error of the best model, which is an unsupervised task. At this point, the reconstruction model is the learned center shape. On the right, you can see a few of these learned models on two datasets. To handle the problem of alignment between shapes, each model is associated with an alignment network, which will learn to align our center shape with the target input point cloud. By doing so, the learned shapes become smoother and can better reconstruct input shapes. We then propose to learn to deform our center shape along a displacement field, to which point is associated a direction in which it can move by varying an amplitude, defining for each point of our center shape a direction in which points can move, which both improves reconstruction and enables us to visualize our linear shape models as continuously indexed sets of shapes. For example, by learning such families on ShapeNet, we discovered a plane which can be continuously deformed from an airliner to a jet. Our final model is then composed of several models, each having an alignment network and several displacement fields. Here, a direction controls the length of the table legs, while another their width. The displacement fields can be either defined with a pointwise learnable 3D displacement field or with an implicit displacement field regarding to the coordinates of points in the center shape. We showed better performances with the implicit parametrization, which results in more uniform displacements. Finally, given an input point cloud X, we predict for each shape model Rk the element that best reconstructs the input. To do it, the projection network P outputs the coordinates A of a shape in a linear family, and the alignment network A predicts the parameters of an affine transformation which is applied to the selected shape. The input point cloud is then assigned to the shape model that best reconstructs it, here highlighted in green. Here you can see a chair which is well reconstructed by a linear shape model of chairs, while trying to reconstruct the input chair with the model of a table has no meaning and results in a bad reconstruction. We train our models end-to-end using a simple cluster angles function, and using curriculum enables us to learn each part of the models step by step. In this figure, we can see how our method handles unaligned datasets. While using only a center shape, the models can't fit well the inputs, and the resulting models are very fuzzy, especially when the dataset is unaligned, where the mean of several shapes has no sense. Thus, the model is unable to learn meaningful prototypes. Adding our alignment network lowers the reconstruction error, while the network learns sharp and informative prototypes for both aligned and unaligned datasets. Finally, the models increase in sharpness and precision while we add displacement fields. This shows that the alignment network allows our model to handle a raw, unaligned dataset to produce a compact overview of its shape diversity. Applying our method on ShapeNet, for example, enabled us to summarize this dataset, to see at a glance that it's composed of several types of chairs, tables, or airplanes, without having to look at all the dataset to know what's inside. This can be particularly useful when considering large shape collections of scans or CAD models, such as the industry dataset ABC. As our models are in the 3D space, they are quite easy to annotate. By doing so, by either manually or using a few training examples, we can propagate their point labels to inputs to perform semantic segmentation of those. We showed state-of-the-art performances for this task on ShapeNet. To conclude, we presented an unsupervised method to represent large point collections as an extension of the deep transformation invariant clustering framework for 3D tasks with learned linear shape models. We showed state-of-the-art performances for few-shot segmentation and introduced a way to easily summarize large datasets of 3D shapes. Thanks for your attention.